Have you ever stopped to wonder what really makes your phone, your laptop, your entire digital life feel so fast? I mean, it's not just about raw processing power. Turns out there's this clever, almost invisible trick happening billions of times a second. Today, we're going to pull back the curtain on caching, the true unsung hero of modern computing. All right, let's get into it. So first things first, let me ask you a question. When you think about what slows a computer down, what's the first thing that pops into your head? The processor, maybe the graphics card, not enough RAM? And yeah, those are all decent guesses. But the real culprit, the single biggest performance killer in almost any machine, it's probably not what you think. Believe it or not, the answer is distance. And I'm not talking about meters or miles here. I'm talking about the tiny but incredibly significant physical gap between your lightning-fast CPU and its main memory, the RAM. To a modern processor, waiting for data to travel from RAM is, well, it's like you having to take a week-long trip just to grab a book off your own bookshelf. It's that slow. And this creates what we call the CPU's waiting game. Our processors have gotten so ridiculously fast that they actually spend a huge amount of their time just sitting there, twiddling their thumbs, waiting for data to show up. This massive speed gap between the CPU and RAM is the fundamental problem that caching was invented to solve. And just look at this graph to see how dramatic that gap really is. For a CPU to grab data from its fastest local storage, the L1 cache, it takes about 1 nanosecond. Okay. From the bigger L3 cache, it's around 13 nanoseconds. But to go all the way out to RAM, we're talking 33 nanoseconds, sometimes way more. Now, these numbers might all sound tiny, but in computing terms, that difference is an eternity. It means going to RAM can be over 100 times slower than the fastest cache. Ouch. So what did the engineers do? They couldn't just magically move the RAM closer. Instead, they built this incredibly clever solution right into the silicon itself. A tiered system, a hierarchy of smaller, faster memory right next to the processor. And this is that hierarchy. You can think of it like a series of express checkout lanes. L1 is the absolute smallest and fastest, holding only the most critical data for each individual CPU core. L2 is a bit bigger, a little slower, kind of like a secondary prep area. And then you've got L3, the largest cache on the chip, which acts as this big shared staging area for all the cores before they have to make that long, painful trip out to RAM. So here's how it all plays out in practice. When the CPU needs some data, it doesn't just go straight to RAM. No way. First, it checks that super fast L1 cache. Is it there? No? Okay, let's check L2. Still no luck? All right, let's try the big L3 cache. It's only if it strikes out on all 3 levels that it finally gives up and makes that slow, costly trip to main memory. Now, when the CPU finds what it's looking for in any of those caches, L1, L2, or L3, that's what we call a cache hit. And this is perfect. It's the best case scenario. The operation happens at lightning speed, the CPU just keeps on chugging, and your computer feels snappy and responsive. But when it doesn't find the data in the cache, well, that's a cache miss. And a miss is a performance killer. The CPU has to stall, wait, and make that long journey to RAM to go get what it needs. The entire goal of this whole complicated system is really, really simple. Maximize the hits and minimize the misses. So this all begs the question, right? How does the cache know what data the CPU is going to need before it even asks for it? It almost seems like it can predict the future. And while it's not exactly magic, it is based on a remarkably simple and accurate principle of prediction. That principle is called locality of reference. It's kind of the secret sauce here. And it's all based on one simple observation. Computer programs are creatures of habit. If a program uses a piece of data right now, there's an incredibly high chance it's going to use that exact same piece of data again very soon, or it'll use the data that's stored right next to it. And the cache bets on this predictability every single time. And this breaks down into 2 main types. First, you've got temporal locality. That's locality in time. The idea is if you use it once, you'll probably use it again soon. The perfect example is the code inside a loop that runs over and over. Then you have spatial locality in space. This is the idea that if you access one spot in memory, you're probably about to access its neighbor. This is tailor-made for things like processing all the elements in an array, one after the other. Okay, so we've been really focused on what's happening inside a single microchip. But what's so fascinating is that this exact same problem and the exact same solution scales up from one tiny CPU to, well, the entire internet. So let's zoom out for a second. So think about it. The problem is identical, just on a much, much bigger scale. You have a fast web service trying to serve millions of users, that's your CPU, and it needs data from a slow traditional database, that's your RAM. The database just can't keep up with the demand. So, what's the solution? You guessed it, caching. And this is where we get the idea of a distributed cache. Now, this isn't a piece of hardware, it's software. You've probably heard of the big ones like Redis or Memcached. What they do is pool together the RAM from a bunch of different servers to create this massive, super fast layer of memory that sits right between your application and that slow database. It serves up all the common requests without ever having to bother the database at all. So what we have now are two totally different worlds of caching. On one hand, you've got the automatic hardware-based cache living inside your CPU. And on the other, you've got this explicit software-based cache used in huge cloud applications. Let's put them side by side and see how they compare. And wow, the differences are huge. Your hardware CPU cache is tiny. We're talking kilobytes to megabytes, and it's baked right onto the CPU chip. A distributed cache, though, it can be enormous, gigabytes or even terabytes spread across a network of servers. That difference in location and size directly impacts speed. Hardware caches operate in nanoseconds. Distributed caches operate in milliseconds. So fast, but 1,000 times slower. But honestly, the most important difference is this last one, management. The CPU cache is totally automatic. You don't touch it. A distributed cache has to be explicitly managed by developers, and that creates completely different headaches. Hardware guys worry about keeping data consistent across different CPU cores, while software developers are up at night worrying about their cache data becoming stale. So after all that, why does this matter to you? Well, because no matter what kind of code you write, understanding these principles, learning to think in cache, is one of the most powerful things you can do to write faster, more efficient software. Here is the absolute key takeaway for any developer. You cannot directly control the hardware cache. You can't tell the CPU, hey, put this specific thing in your L1 cache. The hardware handles all of that automatically. But, and this is a huge but, you can absolutely write your code in a way that the cache's automatic system loves. You can make it work for you instead of against you. So how do you do that? How do you get on the cache's good side? Well, you play by its rules. You lean into those principles of locality we just talked about. When you reuse data you just touched, you're taking advantage of temporal locality. When you process data in order, like iterating through an array, you're giving spatial locality a big high five. A simple change, like processing a big 2D matrix row by row instead of column by column, can make your code 10 times faster. Not because your CPU got faster, but because you stopped fighting the hardware and started helping it. In the end, it all comes down to this one really powerful idea. Caching, whether it's on the smallest microchip or across the biggest cloud network, is all about avoiding slow work. It's about recognizing that the best way to solve a speed problem isn't always to just do things faster, but to find a really clever way to avoid doing them in the first place. And that's a philosophy that can make all the difference, because the fastest operation is always the one you don't have to do.